Softening or spheroidization damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of softening or spheroidization. Based on API 571. Spheroidization is a change in the microstructure of steels after exposure in the 850 degrees Fahrenheit to 1400 degrees Fahrenheit, 440 degrees Celsius to 760 degrees Celsius, range, where the carbide phases in carbon steels are unstable and may agglomerate from their normal plate-like form to a spheroidal form, or from small, finely dispersed carbides in low-alloy steels like 1Cr 0.5 mo to large agglomerated carbides. Spheroidization may cause a loss in strength and/or creep resistance. Softening, also known as spheroidization, is a type of damage that affects metals, particularly in steel. It's a heat treatment-related issue that occurs when the metal is subjected to high temperatures beyond its critical temperature, leading to the breakdown of its microstructure. In spheroidization damage, the metal's original microstructure is altered, causing the carbides to break down and transform into spherical, spheroid, particles. This process occurs at temperatures typically between 550 degrees Celsius to 700 degrees Celsius, which is below the melting point of the steel. Characteristics of spheroidization damage include: Number 1 is microstructural changes. The formation of spherical carbide particles, replacing the original acicular or lamellar morphology. Number 2 is grain growth. Coarse grain formation due to the high temperatures, resulting in a more porous and less dense microstructure. Number 3 is loss of mechanical properties. Spheroidization damage can lead to a significant decrease in the metal's strength, toughness, and hardness. Number 4 is surface degradation. The formation of surface cracks, blisters, or scales, which can compromise the metal's structural integrity. Causes of spheroidization damage include: Number 1 is incorrect heat treatment. Exposure to temperatures beyond the recommended range can cause spheroidization. Number 2 is insufficient cooling. Slow cooling rates can lead to the formation of spheroid structures. Number 3 is high-temperature exposure. Prolonged exposure to high temperatures can cause spheroidization. By understanding the causes and effects of spheroidization damage, metalworkers and engineers can take steps to prevent or minimize its occurrence, ensuring the integrity and performance of steel structures and components. Softening or spheroidization affected materials. Based on API 571, the affected materials of softening or spheroidization are all commonly used grades of carbon steel and low-alloy steels including C 0.5 mo, 1 Cr 0.5 mo, 1.25 Cr 0.5 mo, 2.25 Cr 1 mo, 3 Cr 1 mo, 5 Cr 0.5 mo, and 9 Cr 1 mo steels. Softening, spheroidization, is a damage mechanism that typically affects materials with a specific microstructure, particularly those with a lamellar or acicular microstructure, such as pearlitic steels. The affected materials of softening, spheroidization, can include: Number 1 is pearlitic steels. Steels with a pearlitic microstructure, which consists of alternating layers of ferrite and cementite, are prone to softening due to spheroidization. This includes medium and high-carbon steels, such as AISI 1040, 4140, and 4340. Number 2 is high-carbon steels. Steels with high carbon content, typically above 0.5%, are more susceptible to spheroidization, as they tend to form a pearlitic microstructure. Number 3 is medium carbon steels. Steels with medium carbon content, typically between 0.2% and 0.5%, can also be affected, especially if they have a pearlitic microstructure. Number 4 is some alloy steels. Certain alloy steels, such as chromium molybdenum steels, e.g., 4130, 8630, can also undergo spheroidization, especially if they have a pearlitic microstructure. Number 5 is cast irons. Some types of cast irons, such as gray cast iron, can also be affected by spheroidization, although this is less common. These materials are typically used in applications where high strength, toughness, and fatigue resistance are required, such as in. Number 1 is automotive components, such as gears, axles, engine blocks. Number 2 is aerospace components, such as landing gear, engine components. Number 3 is industrial equipment, such as pumps, valves, gears. Number 4 is construction equipment, such as cranes, excavators. It's worth noting that not all materials with these compositions will necessarily undergo spheroidization, as the susceptibility to this damage mechanism also depends on factors like processing history, heat treatment, and operating conditions. Critical factors of the softening or spheroidization damage mechanism primarily refers to the process that occurs in materials, especially steels, during heat treatment or prolonged exposure to high temperatures. This mechanism is crucial in determining the mechanical properties of the material, particularly its hardness, strength, and ductility. Here are some of the critical factors that influence spheroidization. Number 1 is temperature. The treatment temperature is fundamental in the spheroidization process. Typically, lower temperatures, within the range of a acicular ferrite formation, promote spheroidization, while higher temperatures may lead to excessive grain growth or other undesirable microstructures. Number 2 is time. The duration of exposure to the softening temperature affects the spheroidization process. Longer times generally lead to more significant spheroidization, changing the distribution and shape of carbide particles within the matrix. Number 3 is initial microstructure. The starting microstructure of the material, lamellar perlite, bainite, or martensite, plays a critical role in how quickly and effectively spheroidization occurs. Different initial structures respond differently to heat treatment. Number 4 is alloying elements. The presence of certain alloying elements, such as chromium, molybdenum, or vanadium, can influence carbon diffusion rates and the stability of the carbide phases, impacting the rate of spheroidization. Number 5 is cooling rate. The cooling rate after heat treatment can also influence the subsequent microstructural changes, including spheroidization. Rapid cooling may trap carbon in supersaturated solid solution, while slower cooling allows for more complete spheroidization. Number 6 is stress and strain. Mechanical stresses can impact the kinetics of spheroidization. Stress can promote the movement of dislocations and boundaries, potentially facilitating the dissolution of cementite and promoting spheroidization. Number 7 is atmosphere. The heat treatment atmosphere, oxidizing, inert, or reducing, can influence the surface oxidation of the material and the behavior of carbide phases, potentially affecting the spheroidization process. Number 8 is grain size. The initial grain size of the material can impact its overall mechanical properties and also how easily the spheroidization process occurs. Finer grains may facilitate faster diffusion and spheroidization processes. Understanding these critical factors is important for controlling the properties of steel and other materials through targeted heat treatments, allowing for optimization for specific applications in mechanical engineering and materials science. Affected units or equipment of softening or spheroidization. Softening or spheroidization is a damage mechanism that can occur in equipment and systems that operate at high temperatures, particularly in the context of steam power plants, fossil fuel power plants, and other industrial processes. The affected units or equipment of softening, spheroidization, damage mechanism include. Number 1 is piping and tubing. High-temperature piping and tubing, such as those in steam lines, can be susceptible to spheroidization, leading to a loss of strength and potential failure. Number 2 is boiler components. Boiler headers, tubes, and other components can be affected by spheroidization, particularly in areas with high heat flux and temperature gradients. Number 3 is heat exchangers. Heat exchangers, such as steam generators and reheaters, can experience spheroidization in their tubes and other components. Number 4 is turbine components. Turbine casings, blades, and other components can be affected by spheroidization, particularly in areas with high temperature and stress concentrations. Number 5 is superheater and reheater coils. these coils can be susceptible to spheroidization due to the high temperatures and thermal gradients they experience. Number 6 is valves and fittings. High-temperature valves and fittings, such as those in steam lines, can be affected by spheroidization, leading to a loss of strength and potential failure. Number 7 is headers and manifolds. Headers and manifolds in steam power plants and other industrial processes can experience spheroidization, particularly in areas with high heat flux and temperature gradients. These are some examples of the equipment and systems that can be affected by softening, spheroidization, damage mechanism. It's essential to note that the specific affected units or equipment may vary depending on the industry, process, and operating conditions. Appearance or morphology of softening or spheroidization damage. Based on API 571, spheroidization is not visible or readily apparent and can only be observed through metallography. The pearlitic phase undergoes a time-dependent transformation from partial to complete spheroidization, Figure 4.3 and Figure 4.4. In the case of the 5% to 9% CRMO alloys, spheroidization is the process of transforming the carbides from their original finely dispersed morphology to large agglomerated carbides. Softening, or spheroidization, is a damage mechanism often observed in materials, particularly in metals, that results in a reduction of hardness and strength. This process typically involves the transformation of a material's microstructure, particularly in steels and certain alloys. This process typically involves the transformation of a material's microstructure, particularly in steels and certain alloys. Number 1 is microstructural changes. The first of microstructural changes is phase transformation. The microstructure generally transitions from a more complex arrangement, like pearlite or bainite, to rounded particles, spheroids, of cementite, Fe3C, dispersed in a ferritic matrix. This transformation can occur through annealing processes. The second of microstructural changes is spheroidized cementite. Spheroidization involves the coalescence of carbides into spherical shapes, resulting in a morphology where the carbide particles are rounded rather than angular. Number 2 is particle size and distribution. The first of particle size and distribution is increased particulate size. The spherical cementite particles tend to grow larger over time with prolonged exposure to heat, which can affect the mechanical properties of the alloy. Uniform distribution. The spheroidized carbides are typically more uniformly distributed in the ferritic matrix compared to the initial, more irregular distributions present in as-rolled or as-quenched states. Number 3 is reduction in hardness. As the material softens, there is a noticeable decrease in hardness. This can often be seen in hardness tests, where the values drop significantly when comparing spheroidized samples to hose in earlier microstructural states, e.g., pearlite. Number 4 is visual characteristics. Metallography. Under optical or electron microscopy, spheroidized structures exhibit a more rounded and globular appearance of carbide particles against the lighter ferritic background, contrasting with the linear or lamellar structures seen in pearlite. Fractography. In fracture surfaces, spheroidized materials may show signs of ductile fracture with dimples due to the softer matrix yielding under stress. Number 5 is temperature and time dependence. Spheroidization is typically promoted by long exposures to elevated temperatures. The degree of spheroidization can vary based on the specific temperatures and times used during the heat treatment process. Summary appearance or morphology of softening or spheroidization. Spheroidization is characterized by a transformation to a softer microstructure with rounded carbide particles, leading to a decrease in hardness and changes in mechanical properties. The transformation is predominantly influenced by heat treatment, and the resulting morphology includes spherical cementite particles within a ferrite matrix, observable via metallographic techniques. Softening or spheroidization prevention or mitigation. Based on API 571, spheroidization is difficult to prevent except by minimizing long-term exposure to elevated temperatures. Spheroidization is a phenomenon that typically occurs in metals, particularly in steels, where the elongated carbide structures change into more spherical shapes during heat treatment or prolonged high-temperature exposure. This can lead to a reduction in hardness and wear resistance, which is undesirable in many applications. To prevent or mitigate spheroidization damage, consider the following strategies. Number 1 is optimized heat treatment. Use appropriate cooling rates and heat treatment processes. Avoid prolonged exposure to high temperatures where spheroidization can occur. Implement controlled cooling processes after annealing to limit the time the metal spends in the temperature ranges that promote spheroidization. Number 2 is material selection. Choose materials that are less prone to spheroidization based on their composition and microstructure. Some alloying elements can enhance resistance to spheroidization. Number 3 is intermittent service. If possible, limit the application of high temperatures during service or reduce exposure time to high-temperature environments. Use operational parameters that minimize heating. Number 4 is coatings and surface treatments. Apply surface coatings or treatments that can protect against high-temperature exposure. These can act as barriers to heat transfer or provide thermal insulation. Number 5 is microstructural control. Utilize processes such as quenching and tempering to create a microstructure that resists spheroidization. Maintaining a fine-grained structure and preventing the formation of large, elongated carbides can help. Number 6 is regular monitoring and maintenance. Implement regular inspections and testing throughout the life cycle of components to detect early signs of damage or performance degradation. Number 7 is design considerations. Incorporate design features that minimize heat accumulation and improve thermal dissipation in critical areas prone to spheroidization. Number 8 is use of stabilizers. Consider incorporating stabilizing alloying elements that can inhibit or resist the softening effects associated with spheroidization. These strategies can be implemented based on the specific application, material used, and operational environment to help mitigate the risks of spheroidization damage effectively. Inspection and monitoring. Spheroidization, or softening, refers to the process where the microstructure of materials, particularly steel, transforms into a more rounded shape, usually to enhance ductility. This can occur due to prolonged heating, exposure to stress, or inappropriate heat treatment processes. Detecting spheroidization damage can involve several inspection and monitoring methods. Number 1 is visual inspection. Surface examination. Initial visual assessments of the material can reveal signs of degradation, such as discoloration or irregular surface characteristics. Number 2 is metallographic analysis. Microscopy, optical microscopy or scanning electron microscopy, SEM, is used to examine the microstructure. Spheroidization typically shows a rounded grain structure, which can be compared to a standard sample. Etching samples. Preparing samples with specific etching solutions can help highlight microstructural features, making it easier to identify softening. Number 3 is hardness testing. Number 3 is hardness testing. Number 4 is mechanical testing. Tensile tests, evaluating changes in tensile strength and ductility can detect softening. Deteriorated materials will typically display reduced yield strength and ultimate tensile strength. Impact testing, Charpy impact tests can reflect changes in toughness associated with spheroidization. Number 5 is non-destructive testing, NDT. Ultrasonic testing. This method can identify changes in material property through sound wave propagation. Differences in microstructure can affect ultrasonic velocities. Eddy current testing. This technique can detect alterations in electrical conductivity related to changes in microstructure and can be used for surface and near-surface assessments. Eddy current testing. This technique can detect alterations in electrical conductivity related to changes in microstructure and can be used for surface and near-surface assessments. Number 6 is thermal imaging and monitoring. Thermal analysis. monitoring temperature distribution changes can help identify areas that have been subjected to overheating or prolonged heat exposure, which could lead to softening. Number 7 is chemical analysis. Composition analysis. Assessing the chemical composition of the material can help determine if any alterations to alloying elements have contributed to spheroidization. Number 8 is X-ray diffraction or XRD. Phase analysis. XRD can be utilized to examine crystal structure and stress/strain in the material, which can provide insights into changes associated with spheroidization. Conclusion of inspection and monitoring for detecting softening or spheroidization damage. Combining these methods often yields the most reliable results for detecting softening due to spheroidization. The choice of method may depend on factors such as the material in question, the environment, accessibility, and the criticality of the application. Regular monitoring and inspection of structural components used in high-stress environments are crucial for maintaining material integrity and performance. Thank you.